I, Jagdarsingh, working as an associate professor at Jadhavendra College of Engineering, Punjabi University, Guru Kashi campus, Talwandi Saboo. Today I am discussing the topic antenna array. First of all, we will define what is an antenna. We should know about the antenna. What is an antenna? It is a length of conductor which act as a convergent device. It converts the electrical signal into the electromagnetic waves. At the transmitter, it converts the electrical signal into the electromagnetic waves. At the receiver, it receives the electromagnetic waves and converts back into the electrical signal. So we can say the antenna is a link between the transmitter and receiver. So what is an antenna? It is a length of conductor which converts the electrical signal into the electromagnetic waves. We should know the definition of an antenna. At the receiver, it receives the electromagnetic waves and converts back into the electrical signal. So we can say it is a link between the transmitter and receiver. The physical size of the radiating element is proportional to the wavelength. Higher the frequency, smaller will be the wavelength and smaller will be the antenna size. Assuming that operating frequency in both cases is same, that is in case of transmitter as well as receiver, the same type of antenna can be used as a transmitter as well as receiver. This is known as the antenna reciprocity. Generally, we divide the antenna into two types. First is the omnidirectional antenna, second is the directional antenna. We know that the omnidirectional antenna is that antenna which radiates equally in all directions. If it radiates equally in all directions, then the radiation pattern of this antenna will be spherical in nature. Second type of antenna is the directional antenna. Directional antenna is that antenna which radiates in particular direction. So the in case of directional antenna, the gain is high. The main limitation of omnidirectional antenna is the gain is small, gain is less, because it converts the electrical signal into the electromagnetic waves, and it converts the electrical signal into electromagnetic waves uniformly. Antenna. Now today's topic is antenna array. Antenna array. It is one of the common method of combining the radiations from a group of antennas, in which phenomenon of wave interference is involved. The total field produced by antenna array at a great distance from it is the vector sum of the field produced by the individual antenna of the antenna array system. So antenna array is an arrangement of combining the radiations from group of antennas, in which the phenomenon of how the energy is added, the phenomenon of wave interference is involved. The total field at a great distance from the antenna array, that will be equal to the field produced by the sum of field produced by all the antennas. The relative phase of antenna components depends upon the relative distance of individual antenna of the antenna array. Generally, we divide the antenna array into the two types, that is the linear antenna array and uniform linear antenna array. An antenna array is said to be linear if individual antennas of the arrays are equally spaced along a straight line. If the spacing between all the antennas is same, then the antenna array is said to be a linear antenna array. Individual element of the antenna array is known as the element. So in this case, we can also it called a point source. Next is the uniform linear antenna array. An antenna array is said to be uniform linear array if each element is fed with a current of equal magnitude and uniform progressive phase shift along a line. In case of linear antenna array, the spacing between the antennas is kept same, but in case of uniform antenna array, the spacing between the antennas is kept same and each antenna is fed with a current of equal magnitude and progressive phase shift. Why we use the antenna array? What is the need of antenna array? To increase the gain of overall system. We know that the gain of single antenna is less. If we want to cover more distance, the gain of antenna should be high. So we use the group of antennas to increase the gain of overall system. Second is to get the desired radiation pattern. The desired radiation pattern can be obtained with the help of antenna arrays. We can cancel the side lobes with the help of antenna arrays. So desired radiation pattern in the particular direction can be obtained with the help of antenna array. Next is to determine the direction of arrival of incoming signals. Antenna arrays can be used for finding the direction of incoming signals, from where the signals are coming. For example, loop antenna array can be used for this direction findings. Next is to maximize the signal to interference noise ratio. Since the gain of antenna is increased, so signal to noise ratio will increase with the help of antenna arrays. So antenna array, what is an antenna array? It is a method of combining the energies from the group of antennas. Each antenna, in case of linear antenna array, in case of linear antenna array, the spacing between the antennas is kept constant. In case of uniform linear antenna array, the spacing is kept constant and each element is fed with a current of equal magnitude and the progressive phase shift. Generally, we divide the antenna arrays into the four types. First is the broadside array, second is the end fire array, collinear array, and parasitic array. First of all, we will discuss the broadside array. In broadside arrays, antennas are placed parallel to each other along a line perpendicular to their respective axes. So in this arrangement, antennas are placed parallel to each other along a line perpendicular to their respective axes. Individual elements, the spacing between the elements is kept same. So antenna number 1 and 2, the spacing is D, antenna number 2 and 3, the spacing is D, antenna number 3 and 4, the spacing is D. So the spacing between the elements is kept same. Each element is fed with a current of equal magnitude and all are in same phase. In case of broadside array, each element is fed with a current of equal magnitude and all are, the current is in same phase. In the current flowing through each antenna is in same phase. By doing this arrangement, the broadside array fires in the perpendicular direction. Perpendicular direction means it to the broadside direction. The axis along which the antennas are placed, that is known as the array axis. So this is the radiation pattern of broadside array. Thus the broadside array may be defined as an arrangement in which principal direction of radiations is perpendicular to the array axis, also to the plane containing the antenna array. So in case of, this is the array axis, the axis passing through the maximum radiation through the major lobe, that is called the principal axis. In case of broadside array, this principal axis as well as the array axis both are perpendicular to each other, also perpendicular to the plane containing the antenna. So maximum direction of maximum radiations is perpendicular to the array axis as well as the plane containing the antennas. Next type is end fire array. The end fire array is nothing but same as the broadside array, except the individual element is fed out of phase. In case of broadside array, we know that each element is fed with a current of equal magnitude and the spacing between the elements is same and elements are placed parallel to each other. In end fire array, same procedure is in case of end fire array. In case of end fire array, antennas are placed parallel to each other. The spacing between the individual antennas is kept constant. Each element is fed with a current of equal magnitude, but the in this case the phase shift is there is a phase shift. There is a phase shift of 180 degree. Generally we use 180 degree. Thus, in end fire array, the number of identical antennas are placed equally along a line, spaced equally along a line, and individual elements are fed with a current of equal magnitude, but their phases are varies progressively along a line, such a way to make the entire arrangement unidirectional. In other words, the individual elements are excited in such a manner that the progressive phase difference between the adjacent elements takes place. So, the end fire array may be defined as the arrangement in which the principal direction of radiations coincide with the direction of array axis. In case of broadside array, the principal direction of radiations is perpendicular to the array axis, but in case of end fire array, this principal axis of radiations coincide with the direction of maximum radiations. So, this is the difference between the broadside and end fire array. The difference between the broadside and end fire array is that only each element is fed with a current of equal magnitude and same phase in case of broadside array, but in case of end fire array there is a phase shift between the elements. It is generally of 180 degree. In case of broadside array, the principal direction of maximum radiations is perpendicular to the array axis, but whereas in case of end fire array, the principal direction of maximum radiation coincide with the direction of array axis, So, these are the two difference between the main two difference between the broadside and end fire array. Third is the collinear array. In collinear array, antennas are arranged coaxially. Coaxially means mounted end to end. In other word, one antenna is stacked on other antenna. The individual antennas are fed with a equal current and same phase as in the broadside array. Each element is fed with a current of equal magnitude and same phase. That is also in case of the collinear array. A collinear array is a broadside array in which the direction of maximum radiation is perpendicular to the line of antenna. These antenna direction of array axis coincide with the each axis of the antenna. This arrangement gives the radiation pattern when viewed through the major axis closely resemble with the main lobe everywhere perpendicular to the radiation pattern is spherical in nature, that is circular in nature, and it means it radiates equally in all direction. So, collinear array is also sometimes called as the broadcast or omnidirectional array. The gain of collinear array is maximum when the spacing between the elements is of the order of 0.3 lambda to 0.5 lambda, but this much space between end to end of the element introduces the constructional and the feeding problems. This is the limitation of the broadside array, collinear array. So, if we want to maximum gain, the spacing between the elements should be in the order of 0.3 lambda to 0.5 lambda. The main limitations of broadside array and fair array and collinear array is that we have to feed each element. If we have 100 antennas, ਜੇ ਸਾਡੇ ਕੋਲੇ 100 antennas ਹੈ ਤਾਂ ਸਾਨੂੰ 100 antenna ਨੂੰ ਅਲੱਗ-ਅਲੱਗ ਫੀਡ ਕਰਨਾ ਪਏਗਾ। ਸੋ ਅਲੱਗ-ਅਲੱਗ ਫੀਡਿੰਗ ਪੁਆਇੰਟ ਚਾਹੀਦਾ in case of in case of broadside array and fair array and collinear array. To remove this limitation, we use the parasitic array. In parasitic array, we feed only to the single element, that is known as the driven element. The element to which we feed through the feed line, that is called driven element. Other elements gets the excitation from the driven element. So the elements which gets the excitation from the driven element are called the parasitic elements. So and the array is known as the parasitic array. The main limitation of the broadside and fair and collinear array is that we have to feed individual element. If we have 100 antennas, then we have to, there is a requirement of 100 feed lines in case of broadside array as well as and fair array and collinear array. But in case of parasitic array, there is a need of only single feed line. The element to which we feed, that is called the driven element. The element whose length is 5% more than driven element, that is called a reflector. The element whose length is less than driven element by 5% is called the director. Directors are used to add the energy. Reflectors is used for the reflecting the unwanted waves. The simplest case of the parasitic array is one driven element, one parasitic element generally. In this, the main example of this parasitic array is the Jagdarsingh antenna. Jagdarsingh antenna is also a antenna that is given by the name of the Jaggi and Professor Jaggi and Judah. The parasitic element whose length is 5% more than driven element is act as a reflector, whereas the parasitic element whose length is less by 5% act as the directors. Directors are used to add the energy, reflectors are used to reflect the unwanted signals. Next, we will take the case how the energy from the 2 point sources from two antennas add to each other. So we will take the examples of array of 2 point sources with equal amplitude and phase. In this case, we see that here are two antennas, antenna number 1 and antenna number 2. The spacing between the antennas is d. Suppose the spacing between the antennas is d. We want to calculate the field at point P due to the antenna number 1 and due to the antenna number 2. So the waves from the antenna number 2 will reach earlier than the waves from the antenna number 1 due to there is a path difference 1 dash 2 dash. This is the path difference 1 dash 2 dash. The waves that will reach at point P from antenna number 2 will reach earlier than the waves from the antenna number 1 due to a path difference 1 dash 2 dash. So we will calculate first the path difference between these, that is 1 dash 2 dash. So we will draw perpendicular from 2 to this line, that is 2 dash, and we will draw a perpendicular from this origin to the this line. So there is a path difference, that is 1 dash 2 dash. This distance will be equal to d by 2. This is the angle theta. This is your base, this is your perpendicular. If we calculate O2 dash, O2 dash will be equal to d by 2 cos theta. Here also O1 dash, this angle will also be equal to theta. That is also equal to d by 2 cos theta. So the total path difference between the two waves, that is 1 dash 2 dash, is equal to dy 2 cos theta plus dy 2 cos theta, means d cos theta. So this is the path difference between the two waves. Let one wavelength is of lambda meter. If we assume one wavelength is equal to lambda meter, then how many waves will be in the path difference? How we will calculate the number of wavelengths in the path difference? D cos theta, we will divide by lambda. So number of wavelengths in this path difference 1 dash 2 dash will be equal to d cos theta by lambda. So number of wavelengths in the path difference will be equal to d cos theta by lambda. One wavelength correspond to the phase shift of 2 pi. So one wavelength correspond to the phase shift of 2 pi. So this is the wavelength. When one wavelength, this one wavelength corresponding to the phase shift of 2 pi. So total phase shift will be equal to number of wavelengths. Number of wavelengths कितनी है? Wavelengths is equal to d cos theta by lambda. Number of wavelengths in the path difference, that will be equal to d cos theta by lambda. So phase difference, one wavelength length correspond to phase difference equal to 2 pi. Then total phase shift, phase difference is equal to 2 pi d cos theta by lambda. The number of wavelengths is d cos theta by lambda. One wavelength corresponding to phase shift of 2 pi. So the total, so psi equal to 2 pi d cos theta by lambda. 2 pi over lambda is known as the beta, phase constant beta. So beta d cos theta. So we have calculated the phase shift, phase difference, phase shift, phase difference means psi equal to beta d cos theta. Now so let E1 is the electric field at point P due to the source number 1. E2 is the electric field at point P due to the source number 2. The total field at point P will be equal to E1 e raised to power minus j psi by 2 plus E1 plus E2 e raised to power minus j psi by 2. So this is your these are the two antennas separated by a distance d. This is your origin. So this is the point P where we want to calculate the field. We will draw a perpendicular from here and perpendicular from here. So this distance is d, this will be equal to d by 2, this will also equal to d by 2. This angle is theta. This is your 1, this is your 2, this is your 2 dash, this is your 1 dash. So path difference is equal to 1 dash 2 dash is equal to d by 2 cos theta plus d by 2 cos theta, means d cos theta. Number of wavelengths कितनी हो गई हैं? Is equal to d cos theta by lambda. One wavelength corresponding to phase shift 2 pi. Number of wavelengths कितनी है? d cos theta by lambda. so that will equal to 2 pi d cos theta by lambda. So psi equal to beta d cos theta. This is the phase difference. This is your phase difference. Now the electric field due to the source number 1 is E1. The electric field due to the source number 2 is E2. The field due to this source number 2 will reach earlier, so and field from the source number 1 will reach later. So total field at point P, that will be equal to E1 e raised to power minus j psi by 2. Why we taken the negative sign? Because the field is lagging with respect to origin, plus e raised to power plus j psi by 2. Here we taken the positive sign because the field due to the antenna number 2 is leading. In case of broadside case, in case of broadside array, E1 equal to E2 equal to E naught, means each element is fed with a current of equal magnitude and same phase. So E equal to E1, put E1 equal to E naught e raised to power minus j psi by 2 plus E naught e raised to power plus j psi by 2. Take common E naught. So total field will be equal to E total E naught e raised to power minus j psi by 2 plus e raised to power plus j psi by 2. Now we will divide by 2 and multiply by 2. Divide numerator and denominator by 2. This is the standard formula. So Et equal to 2 E naught cos psi by 2. So total field at a point P will be equal to 2 E naught cos psi by 2, where psi equal to beta d cos theta, where psi equal to beta d cos theta. Beta is the phase constant, d is the spacing between the element, and cos theta. So for simplicity we normalize this. Normalized field will be equal to, if we divide by maximum value, we get the normalized value. Normalized field will be equal to the maximum value of this field is 2 E naught. If we divide by 2 E naught, then we get the normalized field, that is equal to cos psi by 2. Normalized field is equal to cos psi by 2. Now, so E normalized equal to cos beta d cos theta by 2. So the normalized field will be equal to E naught beta d cos theta by 2. Now we will calculate the direction of maximum radiation, direction of minimum radiations, direction of maximum radiations, direction of maximum radiation. This thing will be maximum when cos beta d cos theta by 2 equal to plus minus 1, plus minus 1. The maximum value of sine and cos is plus minus 1. So so maximum value of cos theta is plus minus 1. So cos pi beta, take the value of beta is equal to 2 pi over lambda. The spacing between the elements is equal to lambda by 2, d equal to lambda by 2. So cos beta means 2 pi over lambda into d lambda by 2 into cos theta by 2 equal to plus minus 1.